In this video, we're talking scatter plots, correlation, and testing for significance as maybe a little bonus there. The big conversation is we're looking at ordered pairs, maybe two variables that may be related, maybe not. We're going to talk about how to show that information with scatter plots, and then we're going to talk about how to assess that relationship and talk about whether or not there's a correlation, either positive or negative. We'll do some examples as well to discuss whether or not a relationship exists and what kind of weight we can put on that relationship. Let's dive right in. Let's start the conversation off like this. We'll explore the relationship or ships that might exist between two variables. A simple one that maybe encourage the notion of causation would be somehow price setting may have some influence on revenue or profit. One of the frustrating things that we have to grapple with quite a bit is just because two variables, price and revenue, may be related, doesn't necessarily guarantee causation. In fact, nowhere in this video are we going to assert causation. All we're going to talk about is influence, that one helps predict another. In fact, to that end, when we have these two variables, oftentimes we'll see this expression X and Y. If you've had an algebra class recently, this might be a little throwback for you, that whenever we talk about X, we usually talk about the first term, and then Y is usually classified as the second term. There are other terms we use for these instead. The one variable we're interested in, or the classification between these two, is the explanatory variable and the response variable. The way we like to think about the explanatory variable, often sometimes written as X, is this one helps predict or explain the variable you get in Y, response. Explanatory variable called X comes first, and it should influence or at least be a good predictor of that response variable. Again, doesn't necessarily mean there's causation between these two, but just that one helps predict the other. Let's see some examples. First example, your FICO credit score is used to determine your credit worthiness. It is used to determine whether you qualify for a mortgage or credit card, and is even used to determine insurance rates. FICO scores have a range of 300 to 850, with a higher score indicating a better credit history. The given data represents the interest rates in percents a bank would offer on a 36-month auto loan for various FICO scores. Which variable do you believe is the explanatory variable and which one is the response? Here's the scenario. We have these credit scores. In fact, here's a pair right over here that it looks like for a credit score of 595, they got an interest rate of 18%. Ooh, look at that. Better credit score, 705, got an interest rate of 7%. You might be able to tell from the way I'm phrasing that which one the explanatory variable and which one is the response. When we think about the explanatory variable, that's the X, or the one that hopefully comes first, that explains the response variable, the Y. Even from the bank's perspective, they're sitting there waiting to receive a credit score, so then they can help give out an interest rate. So credit score is the explanatory variable, while interest rate is the response. And the big deal, the reason why it's important that we categorize this correctly, is because if we miscategorize or we mislabel these, well then our model is going to be flip-flopped. And so we need to make sure we can identify appropriately which one helps predict the other. That way when we build our model or our predictor here, we're predicting in the right direction. Give me a credit score and I can output out an interest rate. In fact, when we look at these two, we like to think of them as paired together. In fact, that's really this next term. We like to think of these as paired pieces of data. Instead of just looking at just my credit scores or just my interest rates, instead we look at these as one entity together, my X and my Y together as points, where these have a relationship, they're associated together. Once we have those ordered pairs, and we'll do an example here in a minute, we're going to build scatter plots or diagrams, as they're sometimes referred to. This is just a visual way to represent that paired data. For instance, the example I have here, I have different ages. It looks like 0, 1, 2, 3, 4, 5. And then my response variable that I'm measuring is their height. And so it looks like, and hopefully this makes sense, that as you age, you get taller and taller. In fact, that's what our model would suggest. I have this going up, this increasing notion that they increase together. In fact, this relationship can be talked about in exactly those terms, as positive or negative. Before we get to that though, if you're thinking it's quite a bit to plot, especially you can imagine if you had 1,000 ordered pairs, Excel actually does this very quickly for us. If you want to graph a scatter plot, and this is the instructions here, if you have your data listed, all you have to do is select both of those. You can also select the headers, but you don't have to. You're then going to look into the insert ribbon up top, and then you can see exactly the scatter plot choice. And so as long as you have your data collected, again, no matter how much it is for these ordered pairs, and you select scatter plot, it'll generate for you, ta-da, this nice relationship. Or it looks like these ones are, that doesn't look positive, but we can talk about it. The one thing that you'll need to note here is that whenever you have or you generate these scatter plots, just like when we talked about generating histograms and bar graphs, we have to change the title of our chart. The default is just chart title. That's not very helpful. Let's investigate this positive and negative business I'm talking about here. So we have two types of relationships, at least in the linear sense, and that is positive and negative. And when you think of these relationships, positive and negative, really you can pair this up with the notion we often use is slope. But you can think about it simply as direction. Where are we headed? Well, for that age and height example, these are positively linear related because when I think about going always from left to right, I'm on an upward trend. These increase together versus you can compare that with a negative relationship. This is our credit score and interest rate from before. That is, I get larger and larger credit scores. This is 200 to 400 to 600. Well, then that interest rate comes down and down and down. And so this is a negative relationship because if you go from left to right, that relationship is on a downward trend. These things are negatively linearly related versus positive. There's a couple ways we can measure or talk about this relationship without necessarily having to go through the trouble of graphing that. The primary way we do that is, well, with slope, which we'll talk about later. But right now, we're interested in this correlation coefficient. This is going to tell us a bunch. It's represented with the character R. This correlation coefficient is going to measure exactly what the strength in this linear relationship is. How strong is that relationship? And there are some values to talk about. If you wanted to compute this by hand, I wouldn't recommend it. This is the formula for you. This is a mixed standard deviation over here. The formula is down here. It's quite a bit of a mess. Some of these characters we should recognize. I have X bar and Y bar. Well, those are just sample means of each of their individual columns. And then we have S sub X and S sub Y. This is why we have this little subscript here. It's to denote, hey, this is the standard deviation of just your X data, and then of the Y as well. And so if you can compute these values, some of them you need to compute, well, maybe by Excel if you'd like, but you're working too hard if you're adding and multiplying these numbers together. Instead, we have this very powerful function equals correl. And this will tell you the correlation coefficient, correl, where I need to put in first my Y data and then my X data. And it should always go in that order. In fact, all the functions we'll get for Excel related to this linear modeling always go Y data first, X data second. Let's dive a little bit more into this correlation coefficient and understand the measures or the values that we may get. So one of the friendly things is this R value is always trapped between this window. The smallest or the most negative it could ever be is -1, and the largest is 1. This is the number line. Where look, if R is close to 1, that's going to be a positive relationship because R is positive, but also it's going to indicate a pretty strong relationship. A nice example would be something like if you computed R is equal to 0.81. That's a pretty strong relationship. Now, if we talk about how strong or how significant, well, we'll get into it at the end here. R is close to -1. Maybe R is equal to -0.97. Ooh, that is a very close relationship. In fact, that's very close to a perfect linear relationship. I'll show you a picture in the next slide. And then, of course, if R is close to 0, it's indicating, okay, look, these two probably aren't related. Do not investigate because one does not help predict the other. R equal, let's say, to 0.07. Probably no relationship whatsoever. And so the pictures here go as follows. This is a pretty good relationship, positive. It's going up. I have some funky example in the middle where if I tried to think of a relationship, well, there's no nice line or trend to follow. Probably no linear relationship whatsoever. Versus my last one here, a negative relationship. These are going down together. And these are kind of the three stories that we're interested in. Let me show you a graph where we can investigate exactly these different relationships and maybe get a bit more fine-tuned. Before we get into the graphs or the pictures, though, I want to highlight an important notion here, that there are many ways to investigate a correlation coefficient. A very modern way to do so is to look at separate variables charts and observe trends that are similar. For instance, these things are increasing together or these things are decreasing together. If they're increasing together, that give you a positive R value. If they're decreasing together, that should indicate a negative R value. And there's a couple goofy examples that I want to bring up. The first one is this organic foods. I have a hyperlink here. Let me pull up the hyperlink by clicking. Here we go. This is our chart, or our graph over here, where it looks like we have two relationships, and this is over time. And one is the sales of organic food and the rise in autism diagnosis. And if we look, both of these seem to trend at the same time, that as time progresses, both of these are increasing together, which, my goodness, may indicate some kind of relationship here. But relationship is a tricky word here, because relationship can just mean that they are trending together, that there's some relationship, that maybe organic food sales can help predict an autism rise or decrease, but it in no way indicates any kind of causation. And so, for instance, you can go down here, these are very close together as they trend up, and that R value, very close to 1, they increase together. But just because they are correlated together has no bearing on causation, which is why you often hear the old adage, correlation does not equal causation. If we get this video link is a TEDx talk discussing exactly that big worry that, look, just because two variables are correlated does not mean that they show some kind of causation.
Welcome. I'm here today to warn you about the dangers of ice cream. You may not be aware of this, but these innocent-looking cones full of sweetness are one of the major causes of drownings. And I've got the numbers to prove it. So if you plot a graph of that number of ice creams that are sold, and you compare it with the number of drownings,
positive relationship.
And I think it's very safe to conclude from this that we should ban ice cream, because it's very dangerous. Since you're all smart people, you've probably figured out there's something wrong with my example. What's really happening here is, of course, that there is an underlying factor, which is nice weather, you might have guessed it. And if the weather is nice, more people will go out swimming and unfortunately drown. And at the same time, more people will buy ice cream. And it's not the ice cream that's causing the drownings. And here it's really easy to see that there is something wrong. But jumping to an incorrect conclusion about causality when you see a correlation is the often made logical mistake. And today my goal is to make sure that in the future you can recognize this mistake, and I really hope you can avoid making it in the future for yourself.
It's a great video. A TEDx, an independent TED Talk. It's a great little short if you want to kind of show the dangers of associating, again, correlation with causation. Let's get back to what we were working on. And so there's this dangerous idea that just because things are related, for instance, like the organic food and autism, does not exactly mean that we need to be worried about some relationship between the two variables. Let's dive into our conversation when we were talking about looking at that R value and discussing relationships. This is simply a graph of different R values and how they look when they're plotted together. If R is equal to 1, that is a perfect positive linear relationship. These things are not going to break rank whatsoever. It's a perfect straight line. But notice as I deviate from 1, 0.9, 0.4, my data becomes a little bit more scattered. It moves a bit more. In fact, if you were to try to draw a fence around these values, this would be 0.9, and it's getting a little bit wider because of 0.4. And usually that's about as significant as we're interested. That's a moderate positive relationship. The same is true in the negative direction, that if we have a perfect negative line going down, that's going to be R is -1, and then it gets a little wider at -0.9, a little bit wider at -0.4. Again, the closer to 0, that is a signal that there is no linear relationship whatsoever. And even though there might be a trend, like we see in this last example, a trend does not equal a linear relationship. Certainly we could graph and we could see, but maybe then we shouldn't investigate a linear relationship. Maybe there are other models that we might be more interested in, but certainly we will focus on just the linear. Much like we have standard deviation and variance, that those are similar calculated, but they tell us different things, we have a coefficient of determination, or R squared, which measures, if you think about the variation in Y, right? Y is moving up and down as that progresses, that movement or that variation can be explained by the variation in the explanatory variable. And it's a proportion. It's to tell you, look, how well these variations are explained by one another. The formula is very friendly. It's simply R squared, or the correlation coefficient squared. Here's our example. If the correlation coefficient of the relationship between the number of cups of hot chocolate sold at an outdoor skating rink and the average temperature outside for that evening is R is equal to -0.65, Again, that negative tells you the relationship is going down. That as one increases, the other decreases. On the X, decreases. Which should make sense that the colder it gets, or the temperature, or we can think about the warmer it gets, the less coffee we're going to sell. Those coffee sales are going to go down the warmer it gets. Because again, if it's really hot and warm, nobody's going to want to buy some hot chocolate. How much of the variation in number of cups of hot chocolate sold can be associated, or you can think about that as blamed, with the variation in temperature? Variation, how much can be associated? This is simply a question for r squared, that I have negative 0.65 raised to the second power, or square it, and you should get 0.4225. We think about this as a proportion, or you can even write it as a percentage, that it looks like, what's the explanation here? If I did it as a whole percentage, I would simply write 42%. And so the way we can think about it, here's my little picture here, that we have temperatures. As it gets warmer and warmer and warmer, the number of cups we sell goes down and down and down and decreases. Additionally, I can tell you how well these points are clustered because of that correlation coefficient. But that tells me that, again, this isn't a perfect relationship, that if I know the temperature, I can't perfectly predict the number of hot chocolate sold. But what I can tell you is about 42% of the movement in the number of cups, or the variation, can be explained by the temperature. And so then maybe, and this is something for a future exercise, is we can think about different other variables that may additionally help support the temperature's prediction and the number of hot chocolates sold. Maybe we could talk not only about temperature, but we could say, for instance, the day of the week, or the time of day, or maybe we could try to make some random association with stock price of a certain commodity. There are a lot of different variables that we could try, but certainly 42% is a good predictor. And certainly we can view from our picture, they're certainly well correlated. Here's our next example. A study of bone density on 5 random women at a hospital produced the following results. We have different ages here, anywhere from 37 to 65, and different bone densities. And it looks like one can observe 355 to 320 women as they age at this particular instance. It looks like as they age, their bone density decreases. Let's see if we can get a good idea by plotting exactly these points. For the first one, age should help predict our bone density. So we have the first one is 37. Here's my X is 37. And I should go all the way up, here it is, to 355. Next up, I'm at 41. I'm going to go down a little bit to 345. On 49, we're going to skip a few, and I'll go up to 335. All right, we're seeing that downward trend. Next up, I'm at 61, and that's at 330. There's my next line. And then last, we're at 65, and that's at 320. It's not a perfect linear relationship. I can't make a perfect line through all of those, but certainly I could imagine the relationship, and it's decreasing. It's going down. So before we even compute, would you suspect the correlation coefficient R to be positive, which should look like this going up, or negative? Well, from our picture, these are going down. The line is going down. There is probably going to be a negative correlation coefficient because of the, again, the negative slope. Let's see if we can actually compute the correlation coefficient here. Calculate the correlation coefficient R. If you remember the correlation coefficient, make sure you write equals. And again, if you'd like to open up Excel, you can type as I write here. It should be Correl, C-O-R-R-E-L. And then I want to first enter in my Y data. Again, that should be a cell, comma, cell. For my Y data, that should be bone density. Here it is. That should be starting at E2. And then I want to go all the way to E6. Again, there's only 5 pieces of data there. For my X data, next, that should be D2 all the way to D6. And I should get, there it is, my correlation coefficient, that R is equal to negative 0.9492. And so we can look at that result and say, well, hey, there's actually a pretty good negative linear relationship here. In fact, it's strong. It's a strong negative linear relationship. Now, one thing that should bug us, especially after we talk about hypothesis testing and confidence intervals, yes, these variables are negatively related, but maybe how significant or how important is this negative 0.9492? Can I make this prediction only about these particular women, in which case my model isn't really useful for other people? Or can I take this sample information and then apply it to a larger group? We'll talk about it in a bonus part toward the end here. Next example. So we need to be able to understand, or at least get a good idea on these different R values and how they relate to different pictures. So the first part, match the calculated correlations to the corresponding scatter plots. The first one I have is R is negative 0.7, and I'm looking at which graph. I have 0.45, so that's positive, so I can write a little arrow going up, negative arrow going down. I have 0.06, again, this usually indicates no linear relationship. Ooh, I got 0.92, that should be a super strong positive relationship. The first one to tackle is usually going to be that no linear relationship. As we look at these, I'm trying to identify a trend. It looks like these maybe kind of go upward together, not very strong. Here, this one is going down clearly, and maybe it's okay. Ooh, look at tight and going straight up. This one is that. Those actually like a pretty strong relationship. Oh, here we go. This one does have a trend, but notice it's a little curve. This is looking like no linear relationship. I'll put the one right here for this first one. We then have two positive relationships. In fact, I have two positive R values, R greater than 0. And it looks like the better one is going to be 2, that second graph. All my data is more closely knit together. And then my weaker one is the 0.45, or graph number 3. And of course, the only negative graph is number 4. And that's going to be my fourth graph to identify. And so again, just by looking at a graph, we can determine what roughly the R value is. That's going to help us with our next example. The scatter plots below show the relationship between height, diameter, and volume of timber in 31 felled black cherry trees. We have these two different graphs here. Estimate the correlation R for each graph, or the big idea is which one's higher. Certainly, I'd encourage you to look at this trend and draw maybe a line connecting them. It looks like I have a positive relationship between these two. This is specifically height and the volume. The next one, I can draw a line connecting these two. Ooh, it looks a lot tightly knit together there, is diameter and the volume of that tree. And so for the first one, for the correlation of height, if we had to throw a number on there, again, there are a lot of different right answers for this, but I would say maybe something like 0.6 or 0.6 might be a nice number, just somewhere around there. The actual value isn't important. What we should notice, though, for the correlation coefficient for the diameter, this graph, this should be higher than my height, because again, those points are more closely knit together. This maybe will be bold and we'll say something like 0.87, something real bold. But again, as long as we have that relationship that R for height is less than the R for the diameter, that's going to be an accurate picture. Suppose you have a height of 77 feet, that's a tall tree, and a diameter of 18 inches for another black cherry tree. Which of these variables would be preferable to use to predict the volume? Right, I have these two independent variables. You can write this like x sub 1 for one, and this one's like x sub 2 for a different variable altogether. And if you have to choose one, which one's a better predictor of the other one? Well, notice for our R of our diameter, let's write DIA, is greater than, it's quite a bit larger than my R for my height, meaning that diameter is a better predictor. Better predictor, because they're better correlated together. In fact, if I look at the chart, if I know right about here, 18 inches, well then what are my ranges of responses? That's a pretty small window of options for my volume versus 77, so right about here. Look at this huge range of values for a height of 77 inches. Huge range. That's not going to be necessarily as accurate of a predictor. So we can look at these correlation coefficients and from them accurately pick a better predictor. For this particular example, the higher that correlation coefficient is, the stronger the relationship is, the better it's going to be as a predictor. Higher R value, better predictor. I want to talk a little bit about something that's maybe a little bit extra. So if you'd like to just skip to the end, you're more than welcome to. You don't need this information. But I want to touch on a point that I talked about earlier, that you have a strong relationship, but is that strong relationship even significant? We can get into it. We've talked about hypothesis testing and confidence intervals before, but how does that relate to the correlation coefficient? One important notion to grab here about this correlation coefficient, R, is it's collected based on a sample. Just like we had before, X bar helped us predict the population mean, they're both means, and we had the sample proportion help predict population proportion. So also is R going to help us predict, that's sample correlation coefficient, rho. this Greek character rho that's going to represent how the populations are correlated together. And we'll use to predict and test for significance just like we did in the past. Confidence intervals and test for significance. Let's isolate on just the hypothesis test for now. Consider the hypothesis test that'll go something like this. We need to decide whether the value for the population correlation coefficient rho is close to 0 or significantly different from 0 or not equal to 0. If I was going to write my null hypothesis, what's the status quo? Well, look, we're talking to people, we're saying, ooh, I have a relationship here that the ones we talked about earlier, the diameter of the tree helps predict the volume. So we don't need to look at and somehow measure the volume. If I can get a good understanding of the diameter, we don't need it. And they're like, you're talking crazy talk. There's no relationship between those two. That was just your little sample that you conducted. And you're like, okay, well, I'll prove it for a population. And so the status quo says that rho is equal to 0. There is no correlation, population correlation of those two variables. But we're hoping that rho is not equal to 0. It may be positive, it may be negative, we're not sure. But let's see if we can prove that it's not 0, or at least test for its significance. We need to find a p-value and a test statistic to get that. One thing to notice here is these are pretty small sample sizes. It's going to require us not to use the normal distribution, but instead the student t distribution. So here's our test statistic, and it's with that test statistic that we can generate a p-value. ABS stands for absolute value of t. And the p-value goes like this. We're using a student t distribution. That's what the t is for. This 2t stands for two-tailed, and it's because we're interested in this not equal situation. N refers to our sample pairs, your number of pairs you have, not individual pieces of data, because we look at these as pairs, n minus 2. If you can input that correctly, boom, you'll get your p-value, and fingers crossed, if p is less than alpha, our level of significance, then we can reject that status quo. We can assert, hey, that correlation that I was talking about, I'm not crazy, it's not just for the sample, it's for the population at large as well. So let's see an example where we can test for a significant correlation coefficient, not just in the sample or the anecdotal, but in the population at large. If you remember that bone density example we talked about earlier of those 5 women, we had different ages, different bone densities, and we had an R value, a correlation coefficient of negative 0.9492. And the big question to ask is this even significant? Certainly they're strongly related, but is that a strong enough relationship based on just those 5 women, or n is equal to 5, to say that as a whole, women in this hospital, let's say, have this same exact relationship, that the age will help predict bone density? State the hypotheses for testing for significance, not equal to, for the population coefficient rho. And so I'll write it like this. It should be rho is equal to 0. Again, the status quo is just assumed, dude, this relationship is insignificant. There's no correlation. And what we're trying to show, our alternative hypothesis, is that rho does not equal 0. Now that we've set up the parameters, let's calculate the p-value. Fortunately for us, somebody did the hard work of calculating that test statistic, negative 5.2247. Fantastic. Let me write it like this. It should be equal t dot distribution dot 2t, because this is a two-tailed, because we're doing that equals 2. Then either you can write absolute value, but I'll write out the function like you would type out. It should be ABS, again for absolute value, of negative 5.2247. Woo! And that's my first input. This is just supposed to be absolute value of t. If you wanted to be fancy, you could just type in 5.2247. For the next input, I need n minus 2. N was 5, so we can simply write here 3, or you could write 5 minus 2. And we should get a p-value, ooh, it's pretty promising here, of 0.0136. I'll round it to 4 decimals and round it to 4. And that, well, it should be making us pretty elated. Again, the classic alpha value that we compared to is 5%, and this p-value is looking like 1.4%. If I had to write it to 3 decimals, what can we do with that p-value? With a 5% level of significance, is the relationship between age and bone density for these women at the hospital, not just anecdotal, these 5 women, but for the population at large, is it statistically significant? Whenever we're talking about these alphas and comparing some kind of statistical significance, we always compare p and alpha. In this case, p was 1.4%, alpha is 5%. If you're getting excited, that's certainly the right way to be. this is less than, meaning yes, I can reject the null hypothesis and I can assert or I can accept my claim. Yes, these things are significantly related. We're not just talking anecdotal. I'm not just talking to my 5 friends over here saying, oh, we have a relationship here. Instead, I can make a much more broader claim about the population at whole, that age is a good predictor for bone density, or at least they're correlated together. Now, if I wanted to actually know what that correlation is between the population, well, I could do so with confidence intervals. That would help me predict what rho actually is, using the sample correlation coefficient to predict, again, using a confidence interval of rho, my correlation coefficient for the population at large. Like I said in the beginning of the segment, this population correlation coefficient rho is useful because really anything we take sample, we can turn into a population. In fact, those are confidence intervals and hypothesis testing we did a bunch of. But for this particular example, it's not necessarily as beneficial. Instead, what we'll do is we'll take that correlation coefficient and say, hey, look, if there's a strong relationship, then the model is worth investigating. And the model then is going to talk about the sample. And if we wanted to fill in different sample information, maybe I could do that. Maybe for this particular example, I want to know, hey, look, if I sampled an individual who was 43 years of age, what would be a good idea of what the bone density would be? And a model, if we can track this relationship, would certainly help us do that. But like I said, not necessary, but I think it's important to see an example looking at a population correlation coefficient and being able to understand that, yes, this is a strong relationship, but this relationship only pertains to the sample, not the population at large. Let me recap and wrap with this. The whole reason we're interested in investigating this model is on a small scale, just to see if there's a relationship that might exist between these two variables. But guess what? If there is a relationship, then maybe I can use that relationship or that correlation to say, what if a woman is between these two ages, 41 and 39, on a sample basis? Can I use that to predict what their bone density might be? Or for other examples, like weather helping predict the number of cups of hot chocolate sold, we can maybe use that based on the weather. I can just look at the weather temperature and go, oh, hey, I think this is how much hot chocolate we're going to sell. And we can use these predictors. There are a ton of correlations, relationships that exist between two variables. And hopefully, if it's a good correlation coefficient, like we have up here, negative 0.94, then it's a worthwhile endeavor to build out a model and talk about predicting. So in the next video, we'll talk about exactly how to build that model, some limitations of it, of course, and do some examples as well. Look, if you enjoyed the video, I appreciate the time you put into it. If you didn't, I apologize. For the rest of us, I'll see you in the next one.